I am going to talk not in any great detail, but maybe enough that you'll get some sense of these things about explanatory and predictive models. And I want to start with a discussion that follows on with what Donna was saying about why we develop these models. And so one, and this is maybe the one that's closest to my heart, is to really try to more deeply understand the behaviors that we're working with and the mechanisms of action and influence that modify those behaviors. Because from those deeper kinds of models, one can get to a point of developing new kinds of tools, new kinds of analytic methods, new kinds of measurements that allow us to do things in a much more precise way. More generally, having a deeper understanding from these kinds of models allows us to predict how new technologies will influence those things, to develop, allow us to develop new kinds of design principles. And in the kinds of specific situations that I'll talk about here, having these predictive models, these explanatory models, puts us in a position to really predict the effects of these specific interventions that we're doing in specific contexts for specific people. So in other words, to make behavioral medicine more precise. So I want to start with a motivating example just to provide some context for discussion about the models that I'll be talking about. And this is a system that we started a few years ago called Fittle. It's sort of ancient history now, but it's a mobile health system that was designed to help people change lifestyle by getting them to focus in on changing one individual habit at a time, or maybe two individual habits at a time, mostly focused around diet change and improving physical activity. And following up on some of the comments that Vivek made about the general problems that are facing healthcare in the nation, we have a National Science Foundation grant that allows us to work on this particular project with a collaborator, Kaiser Permanente Hawaii, who's facing exactly the kinds of problems that Vivek was talking about. That is, they have a problem. They have people who are overweight and unhealthy that cost them a lot of money. They have very successful programs for weight loss. 81% of the people who enter into those programs lose weight. One of the problems is that after about 6 months, they come out of those programs and they regain that weight. So there's a long-term maintenance problem. They have really great counselors, really great clinicians, but they only have a handful of them. And so they can deal with approximately 1,000 people per year working in groups. They have 35,000 people backlog who qualify for those programs and want to get into them. So you have this scaling issue. So how can you, and smartphone technology is one way that you could scale these programs out into the real world. And then they have geographic problems. So people actually have to hop islands in order to get to the clinics in Honolulu and Hawaii. Kaiser will pay for those plane tickets because they know that they get the money back after 4 or 5 years if people actually lose weight. And this is very much like the problem that faces a lot of provider organizations in the country, where they have really good programs, they're centralized, but how do you get them out into rural areas or areas that are away from where the centers are? So this particular mobile health application that we started with, Fittle, was one where it was organized around what we call challenges. And so these were, think of them as behavior change programs, where one would start with simpler goals to go after and work your way up to more complex ones. On any given day, you would have some set of goals that you're working on. Here we have some around physical activity and some around nutrition. There were some simple visualizations to tell you how well you're doing, and you're working with a small team. So you've got 5 or 6 other people who are working on similar goals, and there's a team feed where people can text one another. They can post pictures of what they're eating or walks that they've taken. We also had this little AI agent. At this point, it wasn't very smart, but a chat bot that would actually interact with the teams and would interact peer-to-peer with individuals. And on any given day, the main objective is to remind yourself about what you're supposed to do. So here's walking with exercises for 45 minutes. In this case, people are just simply self-reporting whether they did it or not. We have ways of hooking up with Fitbits and Pebbles and things like that. And people could have various alternatives for these goals that were equivalent in various kinds of ways. For any one of the goals, there's lots of information that was written by subject matter experts. So there are these various cards that describe exercises or point you to resources out there in the world. So a very early experiment that we did with a small number of people, we had a couple of these challenges. One was this one that was around essentially for sedentary people in the workforce, getting them up and going and eating a little bit better. And then we had another challenge that was focused in on helping people reduce stress through high metabolic exercise. And these are both 8-week programs. Small number of people, but highly diverse. And the main thing that we got out of this was that we were actually getting substantial improvements. We were getting about a standard deviation improvement pre to post test on stress reduction, healthy eating, physical activities. And the size of this effect is comparable to an effect that you see in the education literature around what's called mastering learning. That is, if you give people very specific goals and you get them to attain one goal after another, you kind of get an effect size that's superior to what you would get with standard classroom instruction. And one of the reasons why we are placing a bet on the idea of personalization is that also in the education literature, there's this finding that if you really personalize instruction, so you have one-on-one tutoring or you have intelligent tutoring systems, you get a 2 standard deviation effect. It's a whopping effect. And so we are making a bet based on an analogy to another discipline, but the idea is that if you really contextualize and really personalize the interventions, you ought to get this big whopping effect. So that's one of the motivations for going after developing these predictive models, because they could drive more personalized and individualized coaching. So conceptually, this is our approach to developing the mobile health applications that we're working on. So we do, as I said before, we have subject matter experts that help us design these programs and provide us with the background knowledge for modifying nutritional habits and physical activity habits. We have an artificial intelligence coaching agent that provides people with specific goals to work on, ecological momentary interventions, so specific interventions to remind them or provide them with information or modify their activities so that they get some personalized interventions. And this coaching engine relies on specific models of the individuals, what we call user models. And those user models are based in part by observing or measuring things that the individual people as they're working through these particular programs. So the coaching engine gives people various goals, they do various things, we do various kinds of measurements, that updates our user model, and then we do some variation on the coaching that's individualized to those people. So I'm not going to be able to go through a complete taxonomy of all the various kinds of models. That's probably an entire course in itself. Let me just mention a few things. So one is there's this kind of distinction that one can make between predictive models versus explanatory models. Predictive models, for those who are familiar with things like correlational techniques, there's a lot of ways that one can get a prediction without having a deep understanding of the causal mechanisms of what's going on. So a lot of big data analytic techniques or statistical techniques sort of treat the data as a big black box. And you can see that if you make a measurement on a particular variable, you might be able to predict something that happens on another variable. But that might not give you a deep understanding of the underlying mechanisms. Explanatory models, to go back to some of the things that Donald was talking about, tend to be organized around some theory. You have some theory that says, here are some things I observe. There are some unobservable mechanisms that are working behind the scenes that make some observations come out at the other end. And I want to build a model of that, and I want to do measurements to either validate that model or better understand that model. But there's a deeper understanding of the machinery involved, and that can have consequences that go beyond just making predictions. There's the distinction between static and dynamical models that Donna talked about. So rather than just have relationships among variables, we want to understand how these measurements and variables are changing over time, differences between stochastic or non-stochastic. So one can make predictions that are probabilistic, that is, I expect some behavior to happen, and maybe it will or won't. Or I can make more deterministic kinds of predictions where I really am making a computation about what's going to exactly happen. Tons of different techniques that come from everything from statistics to artificial intelligence, or cognitive psychology, everything from what one might call regression techniques or Bayesian techniques, neural networks, support vector machines, deep learning. There's all sorts of machine learning techniques. I'm sure some of the folks here could talk for hours about this stuff. I'm going to talk about two very specific models. One is this dynamical control theory model that Donna showed all the boxes for, and then I'm going to talk about some cognitive modeling techniques that we've been using. But just to go back to this distinction between predictive and explanatory, this is a wonderful little device called Orrery, which is a machine that allows one to make predictions about the position of the planets. So it's a little clockwork system, and these are all the little planets, and this tells you all the relationships among the planets, and you sort of turn this crank, and it will give you a prediction about what the relationship among planets will be at any particular point in time. So it's a predictive model. You couldn't really use this to figure out how to shoot something and hit Jupiter 2 years from now. You require a deeper theory that explains the fundamental Newtonian mechanics or the theory of relativity that allows you to understand gravitational forces, etc., to make causal predictions that will allow you to generate something that's never been done before. And that's the distinction I want to make between predictive and explanatory models. So one thing that I think was at least implicit in what Donna was talking about was this notion that one can look at behavioral phenomena at multiple levels. This is a table that I'll attribute to Alan Newell, one of the fathers of artificial intelligence, about a conceptualization of the different levels of human behavior and the underlying mechanisms that are associated with those phenomena. So you can start at the lowest level here and sort of say, well, at the lowest level, there are these phenomena that are sort of at the level of tens of milliseconds, maybe hundreds of milliseconds, that one associates with the biology of the brain. It takes a certain amount of time for a neuron to fire. It takes a certain amount of time for an ensemble of neurons to form a pattern. And those phenomena exist at that level. You can understand them and develop theories about them at that level. At the next level up, the traditional theories of psychology, especially cognitive psychology, things about how long it takes to retrieve memories, how long does it take to process sensory information, how long does it take to form a decision. These are things that sort of take on the order of hundreds of milliseconds, maybe up to a minute, okay? And the theories at that level tend to be about human information processing, thinking of it as a form of computation. And one, again, can mostly develop theories at that level without recourse to thinking about the lower levels, but you can. Then one can move up to these higher levels of where human behavior is organized around goals and tasks, influenced by social factors, etc. These are things that take hours to minutes to days and so on. And here you have a whole set of other theories ranging from behavioral economics, microeconomics, social cognitive theory, etc. And again, there are the way that you think about the variables and the mechanisms can exist within those levels, but again, one could also make recourse down to the lower levels, okay? And you can look at specific models. This is from a paper that Donna is involved with, where here's an attempt to develop a dynamical model around self-efficacy. that relates phenomena at many different levels. So down at the lowest level here, it's at the level of behaviors that are taking place in context, at the grain size of minutes. And what you're trying to do is to predict whether these behaviors will actually take place or not. At the level of the day, one could measure how people feel about their confidence in doing these things on a daily basis. At the level of longer terms, like months and years, there's these constructs about how people view themselves as being of a particular type, an exerciser or someone who is sedentary or whatever. And these variables are related to one another from going from the small scale to the large scale. And of course, then there's large complexes of feedback loops, etc. So this notion that that human behavior is organized at these different levels is one way to think about these things. And there's a logic to it. I mean, the idea is that you have these mechanisms at the low level that must be put together in order to create mechanisms at the higher level. And those hierarchy of systems is a way to look at human behavior and to try to understand it. So let me talk about several models. I'm going to start with some models that are more physically based, just because I think it's easier to understand them at first, and then move on to some that are more psychologically based. So this is a model motivated by the fact that the Rio Olympics are going on, but it's not one that's used in mobile health, but kind of gives you an inkling of how one can develop models and then use them in actual interventions. So this is a physical model of training, and it's called the Banister impulse response model. And the basic idea is, how do I schedule exercise or training sessions so that I can get maximum performance at some point in time in the future? And this model is one that has sort of two components. It basically says, if I give some training, so I get you on a treadmill or I make you run around the track, it affects two variables. One is your overall level of fitness, and another is your fatigue. And of course, these work against one another. And the dynamics of this are slightly different. So it turns out that your fatigue builds up very quickly and decays very quickly. And your fitness kind of builds up a little slower and decays a little slower. And so this is kind of a theoretical graph, but it says, here's a single impulse of training. And it will build up some fitness that will decay over time. And it will also produce an impulse of fatigue that decays over time. And each one of these impulses builds on each other. So if you have lots of training very quickly, it both builds up your fatigue and your fitness, and they also decay. And you can build a little mathematical model that basically says, you sum up all these impulses of your positive gains, and you sum up all these impulses of your fatigue gains, and then your performance is basically the difference between those two things. Okay. And from this, people have actually built software systems that allow you to write optimum schedules of training. And here's some data from an early paper where these are impulses of training, and these are kind of the difficulty of the training sessions. One is for running and one is for cycling. This is theoretically how fatigue is building up and how fitness is building up. And then down here is the actual predicted curves of performance, and then the observed. So you see that it works fairly well. So we did something similar to that in a mobile health application called NutriWalking, which is a follow-on to the Fittle system. And again, this looks a little bit like the previous system. We had various goals that people were working on for nutrition, but we were really focused in on getting people to walk more. One of the additions we had was that as people were failing, if they were failing to walk, we would ask them a variety of questions about whether it was difficult, whether there were things in the environment that were hindering their progress. And underlying the coaching, what we're trying to do is select goals so that we can choose goals that are appropriate for you, so the things that are achievable, and then progress you as quickly as we can to higher levels of physical activity in the shortest term possible. So we would go through a process of, so what we're trying to do is maximize what's called metabolic equivalent tasks. It's basically trying to maximize the rate of physical activity per unit time that you're doing over the course of a week. So what we do is we would ask people a series of questions about what sports they're involved in, flexibility, how much walking they do, and that allowed us to sort of get an estimate of where they are currently in their overall activity levels. Then we have a little agent that sort of says, well, here's where we think we can get to based on American Heart Association guidelines, and we want to maximize your progress towards that. And so we will predict a path that we can take over the course of several weeks that gets you from where you are to where you want to be. And at each point, it's not just physically how much we want to push you, but we're also making a judgment about the probability that you'll actually be able to do this thing. And then we have people doing reporting on a daily basis, and suppose that they're failing a little bit, then we'll intervene, ask questions about the reasons why they're having some barriers to progressing. And then based on that, what we'll do is, if they're having trouble, we'll regress them to a slightly less difficult progression to get them from where they are, where they want to be. If they are doing very well, and if we ask them some questions and they say that it's way too easy, then we'll try to push them a little harder and give them a slightly more difficult ramp. So now let me turn over to some simple psychological models. So I'm going to focus in on a particular construct that is generally assumed to be important in almost all behavior change. And it's this notion of self-efficacy from a theory that Albert Bandura proposed back in the 70s. And it's basically this idea that people have a certain degree of perception of whether they're going to be able to do something, a certain degree of confidence in whether they can do something. And if they're really confident that they can do something, they're likely to do it. And the construct itself has been used as the basis for a variety of interventions. Probably the one that's best known, and certainly the one that we're going to talk about here, is this notion of what's called guided and active mastery. What that means is we're going to work with you to find a goal that you're confident that you can do, that you have a high probability of doing, and then when you do it, that feeds back and increases your self-efficacy so we can give you a slightly bigger goal. So it's kind of guiding you from easily achievable goals to ones that are more difficult. And the amazing thing is it works. This is the model that Donna was talking about. This is a model of self-efficacy based on a fluid analogy. The idea is that you've got these inventories of self-efficacy. So it's like a bucket with some fluid in it, and that fluid can go up and down based on various things that are happening in the environment. That self-efficacy, in turn, influences behavior. So you can think of it as a pipe that goes between self-efficacy and behavior, and as the bucket of self-efficacy goes up, the bucket of behavior goes up too, and it feeds back the other way. As you do positive things, that feeds back and increases the self-efficacy. Now there are other inputs, and that's what all these other lines here are. So for example, another input into the system, so think of it as a tap that allows more fluid to come in, is whether you believe or you perceive that you have good social support from your friends, your family, and whatever. So as that increases, that in turn also increases the amount of self-efficacy you have. And then on the negative side, if you believe that there are barriers that are out there, then that causes a drain. So as you believe that there are some barriers out there, then that drains out your self-efficacy, and that in turn affects behavior. Now, this box diagram is really just a representation of a whole set of equations, a set of differential equations that relate every change that happens in one thing causes a change in something else. So underlying all this is basically just a big set of equations and a computer program that computes how all these things circulate together. I'm going to give you a completely different kind of model for the same kind of phenomena. So this is a model that I've been working on, which is a computational neurocognitive model of self-efficacy. And so the idea here is to move through those levels of explanation that I showed earlier. So self-efficacy theory or social cognitive theory is something that it's a theory that's basically verbally defined at a fairly high level of abstraction. And the point that I'm trying to make here is one where I'm going to take that verbal theory at a high level and map it down to a much finer grained level where we're trying to actually simulate what's going on in the brain that provides the mechanisms for this phenomena to emerge. So the particular theory and simulation system that I'm working with is a system called ACT-R. It's a system that's been developed at CMU by John Anderson and colleagues for many, many years, since the 70s. And it's, on the one hand, it's a theory of the structure of the brain and the functioning of the various components of the brain and how they all interact. It's also a software simulation, so one writes simulations of how people perform various kinds of tasks. And it's, in essence, a simulation system that tells you how the various modules of the brain for goals and retrieving memories and making decisions and perceiving things, how they operate dynamically over time to produce coherent behavior. Underlying all this, just like the previous theory, there's a set of equations that tell you how all these things function together. I'm not going to go through the details, but how long it takes memories to be retrieved, whether memories are likely to be retrieved. What's the utility that people associate with different actions, and how does that influence the choice of the different actions that they make? How do people learn? So how do memories become stronger? How do they fade? How do some choices become more prevalent versus others? So all of that stuff is embedded in a set of equations. Another way to think of this theory is to go back to the dual process theory that Donna mentioned earlier, that it provides a way of understanding the relationship between two parts. One, which is kind of this more slow, explicit, rational decision-making that people do. It's a little more conscious. And the kind of lower level, faster, sub-symbolic computations that are going on computationally. And one of the things that I think is a challenge for everybody here is to understand the relationship between these two things. So when we talk to people, we're providing them with information that they can consciously process and think about. But they are also trying to control this unconscious system that they don't really fully understand themselves. And so a problem for anybody who's interested in modeling and machine learning or whatever is to really understand the relationship between these two things. So the model that I'm going to talk about in a little bit of detail, it was for another mobile health system that we developed to help people with stress reduction through exercise and meditation. And this is a very simple mobile health application. We had people on alternate days would exercise or meditate. On the exercise days, there was a pool of exercises for upper body, lower body, and circuit training. On the alternate days, they had various forms of meditation that they could perform. They had information about the different exercises or the meditations that they were to do. And on every day, they simply reported whether they had done the things or not. We had an experiment where we were trying to contrast whether an adaptive coaching schedule would provide better benefits than one where we had two fixed kinds of schedules, where the idea was over weeks, we would progress people from simple exercises to more difficult ones. In the fixed schedules, they could either have this kind of very easy fixed ramp up, just on given days they kind of ramped up. On another one, there was kind of this difficult ramp up where they kind of very rapidly progressed through more difficult exercises. And then in this adaptive system, there was this very simple little coaching system that would progress you if you were succeeding and regress you if you weren't, depending on the particular exercises that you were performing. So this is just to give you an idea that we had real exercises of all sorts, And we had these difficulty ratings that originally came from expert personal trainers that told us what exercises were more difficult than others. Now, post hoc, after the experiment, one of the things that we did was to try to understand at an empirical level what the difficulty levels of these exercises were. And by difficulty, I simply mean whether people were likely to be able to do them or not. And this is a very simple kind of measurement model called a Rasch measurement model. Our assessment people might actually know what this means, but it's basically a regression. And we just sort of put all the data in, we do a regression of the likelihood that people could do these things, and from that regression, we would know the difficulty of the exercises. So here's another way of looking at this, where at the end of the day, from this regression, we have these parameters that tell us the ability levels of different people when they came into the program. And then for every one of the exercises, there's a difficulty value that we can now associate with it. And from those two parameters, we can predict the likelihood that a person of this ability and an exercise of this difficulty could do the thing that we had asked them to do. Now, what's plotted here is the original expert ratings that we had on those exercises and what we were estimating for these particular exercises, and you can see that they're correlated, which tells us that these experts seem to be in agreement with the actual data that we saw later on. Okay, so here's what people did with our mobile health app in these different conditions. So this is a plot, now that we've empirically estimated the difficulties of these exercises over the course of the 4 weeks. This is what the difficulties were that had been assigned to people in these different conditions. So this is the exercise difficulties for the people in the easy ramp up and for the difficult ramp up that are, both of those are fixed. And then there's this DStress condition where things are adjusting and the difficulty of those exercises is sort of in between those two. This is the actual success in people being able to perform the exercises that we were assigning to them. And the thing to note is that it's in this adjustable coaching condition that people are succeeding the highest, even though they are doing exercises that are more difficult than what the people are doing in the easy conditions. This is an indication, I think, that there's something that's building up in cognitively or psychologically within people that is building up that allows them to tackle these goals that are a little more difficult. So this is what we think is self-efficacy, that by adjusting these things and personalizing them, that we're building up this self-efficacy over time. And now the task is to try to model that stuff. So here's the intuition behind this ACT-R model that I'm proposing here. So the key idea is that we think when people are given these goals, these exercise goals, is that they essentially say, well, okay, you're telling me to do this goal, and I believe that it has I perceive it to have a certain level of difficulty based on my past experience. And now what I want to do is I want to go through my own memory and say, well, have I ever done anything like that? And in particular, have I ever done exercises or activities that are similar to the ones that you're asking me to do? And based on my memory of what I've done in the past, I'm going to have a perception about my self-efficacy. If I've been able to do things like that in the past, I'm going to be confident I can do these new things you're asking me. If I've never done anything like that before, or if I've failed at doing those things in the past, then I'm likely to fail on this thing that you're asking me to do now. And so based on my perception of that difficulty and my own recollection of my own abilities, I'm going to make a judgment about whether I have enough confidence to do this thing that you're asking me to do. This basically fundamentally says that self-efficacy is a memory phenomenon. It's a memory of your own experiences and your own positive activities in the past, experiences in the past. This is just to give you, just to flash at you the fact that this is a real computational program. We have to build representations of the goals that we're asking you to do, including the difficulty levels of those things, and that In the simulation system, it is recording the actual experiences that people have with the exercises that they're doing. So as we trace individuals going through this program, we record whether they succeeded or not, and our estimate of how much self-efficacy we think that person perceived they had at that moment in time. Okay, so we're going to simulate every individual person going through this program. Now, generally, if self-efficacy is a memory phenomena, what kinds of things will we predict about it? Well, the theory itself says that these positive experiences are going to be impulses, just like that physical impulse model that I showed you before. That is, when you have a positive experience, your self-efficacy is going to go up and it's going to decay away with time. So that means that we're going to have frequency effects, meaning that if you've gone to the gym every day for 20 years, that the frequency of those experiences are likely to make you believe that you can positively do something new in the future. Okay, so there's a frequency effect. There's a recency or a lag effect. If you can't remember the last time you did anything positive, then it's not likely that you're going to think that you can do this thing that we're asking you to do. And then finally, there's, I'll call it a stress effect or a stretch effect. If you've really done something phenomenal, then that's likely to have an impact on thinking that you can do something phenomenal tomorrow. Okay, and these are all sort of predicted fairly directly from the theory. And again, think of this as an impulse model, very much like that physical impulse model that I showed you before. So if I have lots of impulses of positive experiences, you exercise every day and you're doing it really well, psychologically, it will build up your self-efficacy like this. And if you don't do it, then it decays away with time. And if we go to the data from that study, we see those general effects. That is, these are just linear regressions. The total number of days that I actually do the exercises predicts whether I'll be successful in the goal that I give you for the next day. If it's been many days since you had a positive experience, then it's less likely that you'll be able to do a goal that I asked you to do tomorrow. And then finally, if we kind of do some measurement of the difficulty of the things that you're doing, the more difficult things that you achieve predict that you'll do something more difficult tomorrow. Okay, so now going down into the details of actually tracing individuals as they go through these programs. So now for every day, we're making a prediction about what an individual's level of self-efficacy is and whether they achieve a goal that was assigned to them. And so here, these data are just aggregated a little bit at the level of days and conditions. This is what the model predicts, whether they will adhere to a particular goal that we gave them or not, and this is what we actually observe. And then again, these are the data. I showed this before. So the black line here is this curve for the adjustable coaching condition. And what if you recall, I said this is the condition where people seem to continue to adhere to goals even though they're getting more difficult exercises. And this is the aggregate model data from all the individual traces that we're doing, where again we sort of get similar, not exactly the same kinds of things. So all of this is to say that that one can develop these models for these unobservable constructs like self-efficacy and treat them in a way where we think of what the underlying psychology is and what the underlying mechanisms are, come to a deeper understanding of what's going on, and also be able to make predictions that hopefully will eventually be useful in doing coaching. Okay, so let me finish up with some concluding thoughts about modeling. And so first of all, echoing Donna a little bit, she made the point that here we have all these great emerging technologies that are giving us this rich, very fine-grained granular data, and this is allowing us to transform these somewhat vague theories of behavior change and turn them into much more precise, dynamical kinds of models, with the emphasis on trying to use those to make very personalized, individualized behavioral interventions. And the bet, as I said early on, is that degree of personalization is the thing that's really going to give us the maximum impact. Now, I want to go over three themes in in general about why modeling can get us to a better place. So one is modeling gives us a way of doing integration. Integration across more unified accounts of how all these different variables are working together, physical variables and psychological variables, to produce the specific behavior that we're seeing and to give us a way of making predictions about how, if we intervene in various ways, that we're going to get specific effects. They give us a way of doing another kind of integration, which is what I'll call decomposition. So we want to get these long-term behavior changes over weeks to months to years. How do we take these phenomena that we want to change at that level and get it all the way down to what we're going to do right now today? And so by having these richer, more integrated models, it allows us to do this decomposition from the big effects we want down to the small, fine-grained effects that we have some control over. And models allow us to say how those small changes will percolate upwards to the bigger effects that we're trying to get to. So understanding that decomposition is important. The idea implicit in all the models that I've been presenting here is that it gives us a handle on the engineering side, which is how to optimize the coaching that we want to do. How do we adapt the interventions in a way that gets us the maximum level of change that we want to get to? And the models give us a way of saying how a specific intervention or a specific individual in a specific context will produce a specific outcome. And then finally, the idea that one comes to a deeper explanation of these phenomena puts us in a position to be generative. And by that, I mean to think of really novel ways, not just taking existing behavior change techniques, but really think of novel ways to do new things. Just to take a simple example, if self-efficacy is a memory phenomena, how do we improve people's positive memories of their past experiences? Well, there's a ton of research on memory in cognitive psychology that says exactly how one can do that. Not necessarily anything that behavior change theorists have done. But again, if you want to go back to my example of the orrery and launching satellites, by getting to a deeper theory, one can get into a position of thinking of new things to do that one would have never thought about doing before. Okay, thanks. And of course, I have a